In this video, I'll talk about gas phase reactions and how fast such reactions can proceed in the gas phase. That's so-called reaction rate. Assume we have two gases, A and B. They can react with each other. How fast A and B react with each other depends on three conditions. First, collisional frequency. A and B must collide to react. If there's no collision, there's no reaction. If there are more collisions, there are more reactions. If we have higher collisional frequency, we'll have higher reaction rate. And also, within the same volume, if we have more A and more B, well, over here, you have a higher concentration of A and a higher concentration of B. Therefore, we have more A's and more B's within the same volume. There's going to be more collisions within the same time period. And therefore, we observe higher reaction rates on the right-hand side. And over here, we have lower concentrations, fewer collisions, and lower reaction rate. So again, the collisional frequency is important, and that's proportional to the concentration of A and the concentration of B. Also, A and B must collide with the right orientation. That's the second factor. For example, the chlorine atom may react with this NOCl molecule to produce chlorine molecule, Cl2, and nitric oxide. For this reaction to take place, the chlorine atom must approach the chlorine side of NOCl. And then these two chlorine atoms can form a bond, and now you have Cl2. What if this chlorine atom approaches the oxygen side of this molecule? There's no reaction. It's impossible for this chlorine to take this oxygen away from NOCl. There are multiple reasons, but one reason is ClO is not stable. Another reason is between this nitrogen and this oxygen, there's a double bond. It's more difficult to break a double bond than to break a single bond. So, several reasons. And there's no reaction. And obviously, it's impossible for this collision to produce Cl2 because physically they are far away from each other in space. And this is called ineffective collision. So we need to have collisions. Higher collision frequency results in higher reaction rate. Also, we need the collisions to happen with the right orientation. What's the third factor? The third factor is energy. For two molecules to react, they often need to overcome a reaction barrier or activation energy. So this is the energy diagram of a reaction. Over here, the starting point is our reactants. This is the products. For the reactants to produce the product, the reactants must overcome a reaction barrier, or so-called activation energy. And then it can form the product. Imagine this is Ellensburg, this is Seattle. It's true that Ellensburg has a higher elevation than Seattle. So if you are driving a car, on paper, you don't need any gas to drive from Ellensburg to Seattle. If there's a tunnel, the car can simply just roll all the way down from Ellensburg to Seattle, assuming the road condition is good. But in reality, there's a Snoqualmie Pass here. That's the so-called transition state or activated complex. So for this reactants to form the product, they have to overcome an energy barrier. And over here, the reactants need to form the transition state or activated complex. And this step requires additional energy. So how do A and B get this energy? Well, one way is heat. If we heat up A and B, they move faster. They have a higher temperature. Remember, the temperature is a measure of the average kinetic energy. So if we heat them up, they have a higher temperature, they have more kinetic energy. That means it's possible for A and B to collide with enough energy and then overcome this reaction barrier or activation energy to form the product. Now I'm going to give you one example. If we mix hydrogen and oxygen gases, the mixture is actually very stable at the room temperature. It may take 1,000,000 years or even longer for this mixture of hydrogen and oxygen to form even one drop of water. But let's say if you provide enough energy with a match, and then it's possible for some hydrogen molecules and some oxygen molecules to possess enough kinetic energy, and they collide with each other, they overcome the reaction barrier, they react and produce water. This reaction is exothermic. That means this reaction releases heat. So heat is released, and this amount of heat can provide enough energy for the remaining hydrogen and oxygen molecules to overcome the reaction barrier and form water. Now let me ask you a question. Hydrogen may combust in chlorine and form HCl. But if we mix hydrogen and chlorine in a reaction container, there's no reaction. And I'm wondering, what are the possible reasons? There are 3 of them. Number 1, maybe the concentrations of hydrogen and chlorine are so low that there are very few collisions. Again, if there's no collision, there's no reaction. If there are very few collisions, well, again, the probability for hydrogen 2 and chlorine 2 to react is very low. And also, if the collisional frequency is low, that means there are very few collisions per time period. Among these very few collisions, maybe they do not collide with the right orientation. So it's possible for these 2 molecules to collide, but the orientation is not right, and they cannot form HCl. The third reason, which is more common, maybe the temperature is just too low. Although the reaction between hydrogen and chlorine is an exothermic reaction, so that means H2 reacts with Cl2 and produce HCl in heat. It's exothermic. However, for the reaction to take place in the first place, you need to provide enough energy for these molecules to overcome the reaction barrier. So one way for this reaction to take place is to ignite it. So again, three possible reasons. If H2 does not react with CO2.